and it's on the paper B2C2P2, which you can see indicated over here. It's the higher tier paper because I'm only dealing with higher tier for now. And these videos are solely designed with one purpose in mind, and that is to ensure that you are able to identify what went wrong in your paper and help you not make that mistake again. So that's what we're doing. All right, so let's move it on. So the first question that all of you decided that, well, not all of you, but some of you, the majority of you, messed up on is question number 2B. And question number 2B is all to do with this item called mutualism. So let's start with that. So Jack finds out about another type of mutualism. Now let's identify what is mutualism. Mutualism is where you have a mutualistic relationship. You're benefiting from something that is living on you, okay, or in you. So for an example, a mutualistic relationship would be you and the good bacteria within you. So that's a mutualistic relationship in that the bacteria benefit from the nutrients that you give it. And conversely, you benefit because the bacteria help you with your digestion. So that's an example of a mutualistic relationship. And of course, a very powerful one. So Jack finds out about another type of mutualism. Leguminous plants have root nodules or bacteria living inside the nodule. So the first thing that's going to throw you with this question is you're going to be like, what the hell is a leguminous plant? So a leguminous plant, just to let you know, it does have root nodules at the bottom of it. And examples of leguminous plants include things like clover, which is a leguminous plant. And it's got bacteria living inside the nodule. Now, that doesn't sound too lovely. It doesn't sound too delightful, but a nodule, as I said, there's little lumps in the root, which contain all these lovely, lovely bacteria. Now, they're saying, why is this an example of mutualism? Well, the answer is very, very simple. Think about the bacteria in there. They are going to be benefiting from the plant giving the bacteria the sugars that it needs to respire. Now, remember, respiration is glucose plus oxygen equals carbon dioxide, water, and energy in brackets, because remember, energy is not a substance. That's why it's in brackets. So now you think of what I've just said, respiration. So bacteria need glucose for the process of their own respiration. So the bacteria benefit from the plant because, of course, they receive glucose from respiration, for respiration, I should say, and they get that from the plant. And explain why this is an example of mutualism. That is because the bacteria themselves contain nitrogen fixing substance or properties, in which case they turn nitrogen into ammonia or directly to nitrates. And of course, as you know, plants need nitrates to make proteins, indicated, by the way. Sorry, I forgot to address you over here. Indicated over here. So if you are at any point not following what I'm saying, please pause the video and have a look over here at the mark scheme. That's why I put it there for you. Okay, so question 3 is the next one that you decided that you were going to imminently mess up on, bless you. So we're going to deal with that. And again, the mark scheme's here should you need it. So please endeavour to have a look over here if you need to. Now, look at the picture of limestone rock. Well, I mean, this is already, floating everybody's boat. It's the most fascinating picture that I've ever seen, surely. I think we may need to put that on Instagram. The limestone formed millions of years ago at the bottom of a shallow sea. Acid rain is now weathering the rock. Ugh. Explain how carbon became locked up in the limestone. That's the first part to your question. Explain how the carbon became locked up in the limestone. And so when you get a question like this, put a slash through the word and, how weathering contributes towards global warming. So there's two parts, how carbon became locked up, and secondly, how weathering contributes towards global warming. So let's deal with the first part here. Explain how carbon became locked up in the limestone. Okay, first and foremost, think about it logically, people. And remember, anything I'm going through is over here. So what we're going to do is we are going to be talking about, first of all, how it became locked up. So you've got the carbon dioxide from your, in fact, I don't know, maybe, no, I'll tell you what, I'll just go through the description for you. Let me make it clear. Carbon dioxide dissolved in seawater. That carbon dioxide is taken up by plants to make glucose, right? Okay, does everybody understand that? To make glucose, right? So that glucose in those plants, if you think about it, sea creatures are going to be nibbling on that. They're going to nibble on the plants, and the carbon that was in the carbon dioxide originally, that's been converted to glucose in the plant, is now being nibbled on by this marine organism, whatever that marine organism might be. Okay, so it could be a sea mollusk of some sort. That's made a lovely little shell out of that carbon now, and it's turned that carbon to carbonates, which are now stored in their shells. And then if you think about it, those sea creatures aren't immortal. They are eventually going to pop their clogs, and they're going to fall to the bottom of the sea. They're going to fall to the bottom of the sea, and all those carbonates in their shells is going to get washed up and eventually turns into rocks. In fact, the rock that you know about is limestone, ladies and gents. There it is, the limestone. So the limestone is the way that the carbonates are now locked into a rock. And remember, they belong to sea creatures. Sea creatures got it from the glucose that they ate, which is made by the plants through a process called photosynthesis. Right, so that's the first thing. Okay, that's the first thing. That will tell you how it became locked up in the animals. Okay, now you think the second part of the question: how weathering contributes towards global warming. So if you're going to get the 6 marks that you deserve over here, and this is for a level 3 part of the question, which is the highest level. Level 2 is obviously lower, and level 1 is the most basic, where you're only going to get 2 marks. Level 2, you get 4 marks maximum, and then level 3, you get 6 marks. And we're always aiming for this area here. So what we're now going to do is we're going to describe how weathering contributes towards global warming. Now you think about it logically. If acid rain, which is the source of weathering here, right? So there is acid rain is now weathering the rock. Acid rain lands on the rock and it reacts with the carbonates. All right, where did the carbonates come from? Remember, from the sea creatures and their shells. The weathering increases the level of carbon dioxide in the atmosphere, because obviously you know that when the acid rain reacts with the carbonates, it's going to any acid reacting with a carbonate is going to release carbon dioxide. That carbon dioxide leads to global warming. All right, that is what happens. All right, and that is it. That is it. So if you then have a link between weathering and global warming, okay, you're halfway there. And if you did the first part of the question, which is how it gets locked up in the shells of the sea creatures, ladies and gentlemen, you've got yourself 6 marks. Right. So hopefully you're very happy with that, and hopefully that should make sense. Okay, moving it on. Question number 4. All right. So let's have a look. In particular, the one that you really messed up on was this one here. So it's all to do with drawing pyramids of biomass. This is for winter. So let's look at the question. Matt, find some information about the biomass values for the lake in winter and spring. Well, Matt, seriously, there are other things that you could be doing with your life. But look, whatever floats your boat. So Matt finds some information about the biomass values for the lake in winter and spring. So we're comparing winter and we're comparing spring. We're looking at the producers, which are things like plants, because they produce their own food. That's why they're called, strangely enough, producers. Primary consumers, which feed on producers, and secondary consumers, which feed on those poor little herbivores called the primary consumers. So if you look at winter, you're looking at winter in particular. We're looking at producers, which are on 4 milligrams of dry mass per meter cubed, 10 milligrams of dry mass per meters cubed of primary consumers, and 2 milligrams per dry mass per meters cubed of secondary consumers. Now, if we then go and take this 4, 10, and 2, 4 always goes at the bottom, because remember, we're dealing with producers. Then it's always primary consumers, which you can see is 10, represented by 5 little squares. And then finally, at the top, you've got your secondary consumers, represented by 1 little square, and that 1 little square represents 2 milligrams of dry mass per meters cubed. So let's look at it logically. So for everyone's 1 little tiny little square, that represents 2 milligrams. So therefore 10 is going to be represented by 5 little squares and 2 is going to be represented by 1 little square. Right, okay. Now based on that principle, for the love of God, it should be fairly simple of how to draw this, ladies and gentlemen. Sorry, I'm just having a look here. And the best way for me to describe this is just for the love of God, look over here. This tells you how to draw it. So if they're asking you now to draw the pyramid of biomass for spring on the grid below. Look up here. Here's spring. 100 goes at the bottom because we're producers. 12 goes in the middle, and 6 goes at the top. The key things that you need to remember are, please make sure you draw the height of the bar the same, just for accuracy's purpose, really. You can see that that's the same height as that, and you can see the top one is the secondary consumers is the same height as the primary and the producers. It just makes it neater, makes it tidier. But moreover than anything else, make sure that 100 producers or 100 milligrams of dry mass per meter cubed is represented by 50 little squares at the bottom. All right, 50 little squares at the bottom. As long as the ratio is the same, then you're on to a winner, ladies and gents. Okay, so just make sure that you've got it the correct proportions mapped here, and hopefully I've read that scale wrong. Because the mark scheme's saying 100 millimeters at the bottom. It's saying, oh, I think I might have read the squares wrong. Because as I say, you can see my screen is slightly different to what it would be printed on paper. You could represent that 100 millimeters at the bottom, 12 millimeters at the middle, and 6 millimeters at the top. What I'm saying is you could also represent it by 50 there, 6 there, and 3 there, if my reckoning was correct with the scale that I see here. So we're both right, okay, but I think it's going to be slightly different on your printed version. Okie dokie, folks. Right. Okie dokie. Unless, no, am I reading that? Oh, I'm reading that wrong. No, Jesus Christ. Yes, it is. It is 10 millimeters across. You get the idea. As long as the proportions are the same as the one here, that's the most important thing. Make sure you're using the same scale and make sure your bars are the same height. Okay. Right. Question 6b. Let's see what other riveting things we have in store here. Okay, so it's talking about, this is 6b here. It's talking about 6b. So 6b is all about subduction, ladies and gentlemen. 6b is about subduction. Now, some of you are thinking, what is subduction? Well, let's have a look. The theory of plate tectonics can be used to explain subduction. What is subduction and how does it happen? And you may wish to draw a label diagram. Right, it's really, really simple. I'll tell you what I'll do. Let me show you what it would look like in the book over here. Structure of the Earth is where you find it. There it is. Okay, here's subduction. Okie dokie. Right, subduction, ladies and gentlemen. This is subduction. Now, it's really important you understand we've got 2 plates. We've got the oceanic plate, or the oceanic crust, which is heavier. It is more dense than the continental crust here. You can see continental's labeled clearly. Continental here is lighter than the oceanic. So you can see when these 2 plates collide together, you can see the oceanic goes underneath, and you can see that the plate will or the crust, I should say, will melt. It'll melt. And when it melts, that rising magma will then come out as a volcano. And that will happen on the continental plate. Now, this whole process here, sorry, oh, my mouse isn't working, this one here is called subduction. So this is the subducting oceanic plate, and it's melting as it goes down. So hopefully that should now be very, very clear to you of how that actually works. And remember, the whole process, guys, is happening. Sorry, I'll go back to the diagram for you. The whole process is happening in the first place. This isn't just happening because nothing is moving underneath it. This is happening because underneath here, there are convection currents. Look at what my mouse is doing here. There's convection currents going round and round and round, and that is obviously going to be dragging slowly the oceanic crust down. So there's a number of things that you need to mention in summary here. you've got to be able to mention that the convection currents are moving the plates by circulation in the mantle. You need to be saying oceanic plate is more dense, and you therefore need to say that the oceanic plate therefore goes underneath the continental plate. Okay. If you also said it starts to melt, that's a bonus there. I mean, I've already stated 4 points there, and you only need 3 of those 4. All right, so moving it on. Question number 10. Okay. The question number 10 is this when it finally. Oh, here it is. Okay. So question number 10. Again, please, if you do struggle and you want to have a look at the mark scheme, it is all here, ladies and gentlemen. It is all here. I'll have to reduce that a little bit for you so you can all see it clearly. It is all here for you as well. So please, if you lose track of anything I'm saying, then have a look over to the right-hand side. Sodium chloride, or salt, is a very important chemical. Well, it is, because it makes your fish and chips taste delightful, and obviously curries would just not exist without this lovely, lovely substance. Okay, so concentrated sodium chloride solution can be electrolyzed to make useful products. Look at the diagram below. This shows how this can be done in the laboratory. Okay, right, so there's your concentrated sodium chloride solution. You can see that there is some kind of a beaker type substance here. You've got a positive electrode, you've got a negative electrode. And you should remember the positive electrode is always called the anode and the negative electrode is called the cathode. Sodium chloride solution contains ions, sodium, chlorine, hydrogen, and hydroxide. And you notice that the charge on them is that's a positive, that's a negative, that's a positive, that's a negative. Straight away, your brain should go, oh, okay, that's a positive. So it should probably and go towards the negative in some way. Chlorine is negative, so it should be going towards the anode. Hydrogen is positive, so it should be going to the cathode. And hydroxide is negative, so it should be going to the anode. What happens during the electrolysis of sodium chloride? Concentrated sodium chloride solution. And your answer should include equations for the reactions at each electrode. Use E to represent an electron. So fundamentally, if you want top marks, you better be including those equations. If you want basic marks, you want to be just talking about what's happening here. Okay, so that's just as a general rule. Okay, so let's deal with this first and foremost. I'm going to show you what's going to happen. So what we've got here is we've got a very real situation, and I'm just wondering, shall I explain this or show you a video? No, I'm going to explain this, so watch. I'll tell you now straight off. You just need to remember what I'm just about to say, okay? Chlorine is a gas, hydrogen is a gas. There are more of those in there, really, than the sodiums or the hydroxides. So I'm telling you now, you just need to remember that the only things that are going to move and form a gas will be the chlorine, and the chlorine is negative, so it'll be going towards the anode, and that means that chlorine gas will form here, and hydrogen gas, which is also very plentiful and very, very light indeed as well, will go over here. Okay, and what it does here is the hydrogen, which you can see is positive, is going to be picking up a negative electron. Right, well, how do you represent that? Watch. Okay. Hydrogen is going to pick up electrons to form a hydrogen molecule. Okay, does everybody understand that? Hydrogen ions will go over to the cathode, where it'll pick up 2 electrons and it'll form a hydrogen molecule. Now, why is it even got, I'll tell you now, why is it a hydrogen molecule? Because remember, hydrogen is covalently bonded and it always travels in pairs. And because of that reason, you need to kind of balance this correctly. So if there's going to be a hydrogen molecule, you can't just have 1 hydrogen ion there, you need 2. And for 2 hydrogen ions, obviously you need 2 negative electrons. Why do you need 2 negatives? Because you need to balance out the 2 positives there, and that's why this little baby over here has no charge. Then now, as I said to you over here, with the chlorine, it's a negatively charged ion. It's going to go over to the anode. So at the anode, this is what happens. Now, once again, you're probably thinking, why is that 2 chlorine ions? Well, the answer is because chlorine also travels in definitely travels in oh, why am I going here? Over here. It travels as a diatomic or two atoms together, because remember, chlorine is in group 7, and therefore they share electrons if they're a non-metal. Okay. So two chlorine ions will need to get rid of, there's the minus sign, 2 negative electrons to make a chlorine molecule. And that is happening at the anode. All right. So what's left? You've got the sodium and you've got the hydroxide. So obviously the only thing going to be left over, ladies and gentlemen, is sodium hydroxide. And that sodium hydroxide is very useful because, of course, it can go on to make things like bleach, and it can remain to make things like soap and so on and so forth, and drain cleaner, which is always great when you're trying to get a mass of soap, lava, hair, and God knows fat and dribble and God knows what else from your sinks. So that is very, very useful. And so we can't undermine this process. It's very important. Okay. Righty ho. There we go. Question number 11. I hope you can realize I've got a little bit of a cold here, so I hope you understand how altruistic and wonderful I am for doing this for you. Or dribbling and dying. Very vocally, I might add. So number 11B, Polly, here we go, what a great name. Polly and Oliver, very posh. Polly and Oliver were talking about the factory that is near their home. God, these are interesting discussions, aren't they? Polly said that the factory produces dangerous radioactive waste. Now, that would be something interesting, actually, because I'd probably either migrate or try and chop off that third arm that is growing. It's not appropriate. It does nothing for one's love life. So, Polly said that the factory produces dangerous radioactive waste. Oliver said that if the waste was put into thick aluminium cans, it would be stored safely. Is Oliver correct? Right. You could have two answers here. Two. And both of them are going to get you the mark. If in that container, in that aluminium container, you've put something that's only giving off alpha or beta radiation, there you go, alpha or beta radiation, then yes, it's fine. It could be stopped by thick aluminium. But if you assume, as I would, as many of you should, that that Polly is referring to gamma radiation coming out of those cans, then what I would say is no, because gamma can penetrate aluminium. And remember, gamma can only be stopped by thick lead. So it depends on who you align your opinion to as to whether you get this right. And as I said, both of them are correct. Okay. And numero 14, ladies and gentlemen. Here we go. Okay, number 14. Sam wants to reduce his energy costs. Now that is important because let me just move it onto the mark scheme so you guys can see what I'm talking about over here. Sam wants to reduce his energy costs. He fits a wind generator to his house. There it is, the offending article. And the generator produces 1.8 kilowatts per hour of energy each day. And remember, one day, if you don't know this, you should probably go back to primary school. It's 24 hours. So calculate the average power output for the generator in kilowatts. Now, I am telling you this, right? The minute I see a question like this is going to be a calculation. Calculate the average power output of the generator, right? So I would go right back to the beginning. Power. Okay. Power. Okay, they haven't given you the voltage, they haven't given you the current. They haven't given you the work done, they haven't given you the time. So I'd go, okay, I don't need that formula, and I don't need that. Where is it? I don't need that formula. Sorry, this one. I don't need either of them, but I do need this one. Energy supplied is power times time. Okay, they've given me the time, which was 24 hours in the question. What are they trying to do? Oh, yeah. They're trying to get you to work out the power output, and they've given you the energy supplied, which is 1.8. Now, very, very simply, rearrange the formula. Put it into a triangle. Put it into a triangle. I'm doing a triangle over here because I can't draw one, okay? But put it into a triangle. Power times time is going to be at the bottom because they're next to each other. Power times time. And then over here is going to obviously be energy supplied in my triangle. So if I'm trying to work out power, I need to do energy supplied divided by time. Energy supplied divided by time. The energy supplied was 1.8 and the time was 24 hours. Now, let me go back to the question. So 1.8 divided by 24, ladies and gents, is 0.075. Put it into your calculator. There it is. It's 0.075. So 1.8 divided by 24 would give you 1 mark if you only put the calculation, but you would get both marks if you put the correct answer. So that's how you answer that one. Remember to keep using the formulas at the front, and if necessary, turn the goddamn thing into a formula triangle. Don't complicate life for yourself. If you are a very, a competent mathematician, you may be able to just do that without doing a formula triangle. But I think for ease of use and for time, sometimes people prefer to use the triangle method. Electricity costs 16 pence per kilowatt hour. How much money will Sam save on his electricity bills per day? So very simply, how much will he save on his electricity bills per day? If it costs 16 pence per kilowatt hour and it's producing 1.8 kilowatts per hour, then what we've got is 16 times 1.8, which should give you 28.8 pence. Okay, and the final question for today is a factory needs 100 kilowatts of electrical power to operate its machinery. Energy is wasted in transmitting the electricity from the power station to the factory. Look at the data showing the effect of using different transmission voltages for the power cables to the factory. Right, so let's read the question. 10,000 volts is the most efficient voltage for the transmission of 100 kilowatts of of electricity. Explain why. Straight away, transmission voltage, look at 10,000. Look at the energy wasted. Jesus Christ. Lord have mercy. It's the easiest question in the world. It's 2 marks, right? It's got the least energy wasted, okay, for each kilometer of cable, very simply. So if it's got the least amount of energy wasted, then it's going to have the lowest current, okay? It's going to have the lowest current. Highest voltage means the lowest current. Highest voltage means lowest current. Look back on your revision guide if you need to confirm this. If you carry voltage at a high voltage, the current in the wire stays low. And that means that less energy is lost through the heating effect. So that's why the power station keeps the voltage so high. Okay, and I think, guys and girls, I think that's pretty much it. According to your teachers, that is your paper completed. I'm just having a look for any others that could have been problematic in there. Because usually those 6-mark evil buggers are the ones that get you guys. And I've done 2 of those 3 6-markers. So I think I'm happy with that, and I hope you're happy with that. Ladies and gentlemen, good luck with your revision. You are expected to try the questions out for the booklet that's been produced. Not all of them. Some of them might be the same questions, but not all of them are the same questions that are in this mock. And they've been chosen for you specifically because, as I said, most of you underperformed in the questions that I had been through. Hopefully you'll find that video useful, and please subscribe and like the video because I'd like you to do that. It's just as simple as that. All right, best of luck, guys. Take care of yourselves and good luck for everything, okay? Bye-bye. Take care.